So our last speaker of the conference, we are very, very happy to have here Nikolai Vladimirovich Krylov, who is now a professor at the University of Minnesota. So please, the stage is yours.
Thank you. Thank you for inviting me. I will give a talk not as a not about stochastic partial differential equation, but about their friends more. So, and by the way, I retired from the University of Minnesota 2 days ago. So that, but so I'm retired. What the talk is about diffusion processes with drift in a Morrey class. A Morrey class which contains d+2. D is the dimension of the space, and so the whole thing starts like that. That we have a Euclidean space. These are points, complete probability space, and blah blah blah. And what is important is that S delta is the set of d times d symmetric matrices whose eigenvalues are between delta and delta to the -1. So uniformly non-degenerate. Now, assumption what the object we are working with is a rather can look strange and trivial. We have a S delta valued function sigma tx smooth. So smooth in t and x as regular as you like. And the smooth are devalued function, this was drift with compact support. My goal is to obtain some estimate, which estimates which are independent of how smooth sigma is and b is. And the fact that I'm considering this stochastic equation instead of just stochastic integral without dependence on depending only on omega and r. And the fact that this is the such a simple equation allows me to obtain my estimates. In the more general case, I don't know how to do that. So I consider the system. There is TR, but this coordinate is just time. So TS is T plus S, and T is starting point for time, X is starting point for XS. So that the couple TRXR form a strong Markov time homogeneous strong Markov process. You may say that it's time inhomogeneous. No, it's time homogeneous. The only thing is that the one of coordinates of this process moves with speed 1. That's it. So we have a strong Markov process TSXS, and the goal is to present conditions on the drift of Morrey type with mixed norms, which allows to obtain Alexander type estimates for potentials of TSXS in spaces with mixed norms. And for instance, when the function is just in a LD0 plus 1, then LD0 plus 1, when D0 is less than D. So if you know Alexander estimates, parabolic Alexander estimates are proved when the function, the right-hand side of the equation or the function under the integral sign is in LD plus 1. But however, they hold for degenerate or non-degenerate processes and in a very large class of cases. In my case, I have strongly non-degenerate equation, and this D0, this depends on on delta on the so we take two couples of numbers p0, q0, which are in from 1 to infinity, infinity included, satisfying this equation and this equation. They are the same, but this condition will be imposed on the drift, and this condition will be imposed on the right hand side on function f. And what is interesting is that drift will satisfy this condition, right hand side will satisfy this condition, and still the equation holds. And p0 and these are different, could be different. So d0 is the function of the dimension and the non-degeneracy constant. And now usual, more or less usual notation. This is the ball of radius r. This is ball centered, this centered at the origin. This is center x. This is a cylinder, height t, capital T in time, and radius r. Then this is a shifted cylinder, and this CR is actually height r square in time, and r and ball of radius r in x in the space. Now this Gothic CR collection of all cylinders of radius r, I call this r radius of the cylinder, although, well, just radius. And C is the collection of all of them. Now, what is the condition on the drift which I impose? You take any cylinder of radius r, and you take the norm P0, Q0, which I will describe you in a moment, and require that for any ball, this be less than b hat times r to this power. This kind of complicated condition can be understood more easily if you write it in this form. What is this? This is just a normalized norm, average norm. So this thing, when you plug in 1 here, is 1. So actually, this is the norm of this one divided by the norm of function which is identically equal to 1 on the cylinder. So basically, this is the average norm of B is less than B hat times r to the minus 1. And what are the norms? The norms, if P is bigger than Q, then the norm is defined more or less as usual. You first integrate with respect to X, and then with respect to T. But if P is less than Q, it's the other way around. You first integrate with respect to T, and then with respect to X. I didn't see any application of this norm, actually. In one of my papers, norm of such time appeared, indeed, and in this paper I couldn't use this norm, but this is a very peculiar situation. So to remember how these norms are organized is that Q is always related to the integration with respect to T, x with respect to p related to the integration with respect to x, and the power here of the interior integral is always less than or equal to 1. So that this is, and now two main results of the talk. By the way, what I'm saying that since B is bounded and has compact support, such a B hat satisfying this equation exists, so that it's so under assumption 1-1, assumption 1-1 is just nothing, more or less nothing. That this is that they're smooth and compact support. So there is a constant B hat depending only on the dimension delta, such that if the condition, this condition holds, this condition holds for all R, for any R in 0, 1, and or any cylinder, then for any R and Borel F, we have this estimate where tau prime R is the first exit time of XS from BR. So this is the this is what I'm saying, what is right hand side or function f inside the integral. For any non-negative, yes, non-negative f, you have this estimate where this n depends only on n and d and delta, and so that actually doesn't matter how smooth or how bad, or if you have bad coefficients and you approximate them with good ones, then for the equation with bad coefficients you will have the same estimate, provided that this constant is independent of your approximation. So in this situation, we require, so B hat is sufficiently small. We require this to be sufficiently small for all R's. It turns out that this global condition for all can be replaced with the local one at the expense of losing good control on the factor of the norm. And exactly this is the thing. Take R0 in 0 infinity and assume that there is a constant, then under assumption there is a constant B hat depending again only on d and delta, such that if this condition holds for any R restricted to 0, R0, and cylinders of the radius R, then for for any R from 0 to infinity, you have this estimate with n hat, where this n hat depends only on d, delta R, and R0. So now some discussion or application. I assume that we are now given the same assumption, but no smoothness. We just Borel function as delta value, Borel function sigma, and Borel B, and this estimate holds with B from the theorem or theorem 1. Actually, this B hat is the same in theorem 1-2 as in theorem 1-1, and this theorem 1-2 is derived from theorem 1-1 pretty easily, actually. Theorem 1-1 is non-trivial result. So we want condition 1,4 to be satisfied with be hat for restricted R. And what's the claim? The claim is first I introduce the operator, the operator corresponding to my coefficients. A now is 1/2 sigma square, and now I need the notion of the parabolic boundary. So if you have a domain, then domain in RD+1, so domain in the space and time, depending on where space and time vary. One we denote by d prime q, its parabolic boundary. And parabolic boundary is defined as the set of all points on the boundary, which are endpoints of continuous curves of this type, txt. T in AB, some AB, have nothing to do with this one, which start in X, in Q, and belong to Q for all T less than B. And these are endpoints, so they're on the boundary. And let me try to draw a picture if I can. There should be, yes, annotate, yes, there is something. Not text, where is the line? Draw, okay, I see. So you imagine that you have a domain like that. So t-axis is here, and the x is here. What will be the parabolic boundary here? So the thing is that you can reach these points from inside, and the curve will be type of txt. But you will not reach this one. So this is not part of parabolic boundary, and everything else is indeed can be reached from inside the domain by a curve of the type txt when t varies and xt varies in this direction. Now clear. And why didn't it clear? Okay. So this is our parabolic boundary, and now W12PQ is the set of functions such that this derivatives function itself belongs to LPQ locally in Q. Then here is the parabolic Alexander estimate. So we have a domain Q, which is in R times BR. So this is a cylinder, infinite cylinder. But we assume that Q is bounded. And function belongs to the W12PQ. So and this PQ are different from the ones which were in this one P0 Q0 in the condition 1,4. PQ in this space and C is a function, but actually, I mean, a measurable function bigger than 0, no condition. Then what we have is you have that u is less than this quantity. And usual parabolic Alexandrov estimate is when here is LD+1. Now it's LPQ and PQ both can be less than D+1. They can be equal to D0+1, and D0 is less than D. And times sub of U plus over the parabolic boundary. So in particular, the maximum principle, if this thing, this operator is bigger than 0 in Q and U is less than 0 on the boundary, then U is less than 0 in Q. The proof is the proof is obtained by using the Ito's formula. Although there is trouble because the coefficient, the drift coefficient is bad. So and then so that we actually then approximate B by using modification, and which preserves this condition 1 for which is easy to see that it preserves this condition 1 for with the same constant. One can adapt this theorem to obtain the elliptic Alexandrov estimate, and this shows advantages of having mixed norms estimate for parabolic operators. So what you do, so I will denote by LP either LP over RD or over RD+1, but and you'll see each time easily which LD is used. So in this theorem, this LD0 is LD0 of RD. So we now assume that A and B are independent of time, and P is equal to P0 and D0, and Q is equal, both Q's are equal to infinity. So then take a function C bigger than 0, and then you have on O, this is a bounded domain. This is more or less the usual Sobolev space, local. Then you have this is parabolic elliptic Alexandrov estimate, but with LD0. And I outline here the proof, although the proof actually ends here. You take this function and apply the previous estimate in this domain. Then what you obtain is this estimate. What you do then, you let epsilon go to 0, and that's it, and you get the result. So and this is possible because I allowed in the previous theorem Q and Q0 to be infinity. So now some history may be more interesting than and an example more interesting than the result itself. In the case when d0 in the previous theorem, in the last theorem, is replaced with d, and the result belongs to Alexandrov, and this is 1960. Many people think that this result belongs to Backelman also. No, Backelman didn't consider drift at all. So, and our all main emphasis is on relaxing condition on drift, and of course on the right hand side too. So this is in the paper in the Clade, and the proofs were given in 1963. Our theorem extends Alexandrov's result in reducing the power of mobility of both the drift and the free term. However, we treat only the uniformly non-degenerate case, and in the Alexandrov's estimate, he allows degeneration, but then the estimate is more involved, but still there is. Since Alexandrov estimate, there was a considerable interest in reducing the LD norm of the free term to LD0 norm, with D0 less than D. And this was done by Cabré in 1995. And then for bounded Cabré for bounded and Fogg in 1998 for being a d plus epsilon. And recently I allowed B to be in LD, and not in LD no LD0 as now, but in LD, and the free term in LD0, LD0 less than D. This made it possible to develop a W2P solvability theory with P less than with P say equal to D0 for linear equation with B in LD and P less than D. Applied to fully nonlinear equation, we can now treat W2 D0 solvability, and this is done in this paper, also a recent paper, and they are all on arXiv. In Theorem 1.6, and this is the joint paper of my joint paper with Hans Redong. Theorem 1.4, this elliptic Alexandrov estimate is proved, loosely speaking, when P equal P0 and equal to D0, so that indeed drift is also not summable to the power D, but summable to the power D0 with this condition 1.4. But R0 is comparable with the diameter of O. And in this case, which I present now, it's R0. If you have R0, then no matter what the diameter of O is, there is an estimate. By the way, it's a very interesting thing about the smallness. I assume that hat B is small enough. Observe that if, say, let's concentrate on elliptic equation. For parabolic equation, unfortunately, I don't have any example. Any example showing that something is impossible. If you take a B, absolute B such that absolute value is C or absolute X with small enough C, then B satisfies assumption of theorem 1.4. So that indeed there is B hat such that depending on C actually equal 2c times a constant depending on the dimension. So that the condition is satisfied. At the same time, this is not in LD. So that it's indeed weaker. One might could think that once I impose condition on B with D0, but condition 1,4 requires certain decay of the norm of B. Then it could be that the only functions which satisfy this equation are just in LD. But no, this is an example. And even more, look at this situation. Take U to be 1 minus x absolute value of x squared, so that this is function in the ball of radius 1 is strictly bigger than 0 on the boundary, and take this B, so that absolute value of B will be equal to this one with C equal to D. So then very simple computation shows that this holds, and U is 0 on the boundary. Then common sense says that U should be 0 everywhere, but it's not. So what is wrong? This satisfies condition, but this C is not small. Condition 1,4 will be satisfied with some B hat for this B, but not small B hat. If you take it, actually what happens if you take this constant smaller, then the maximum principle holds for such B, and you see that AIJ, it's just identity matrix. One more result which I want to mention is that there is a recent paper of mine where I considered this F in LPQ. No, wait, forget about LPQ. Consider this equation, and B is in LD plus 1. What are the difficulties? I said that I can consider even B is in D0 plus 1, but satisfying condition 1.4. And what is generally the difficulties here? If B is only in LD plus 1, then from where you where do you hope to find U? This term is at most, at best, in LD plus 1. So your best guess would be U in W12 D plus 1. Okay, U in W12 D plus 1, then the gradient is not bounded for such functions. It's not bounded, then this is not an LD plus 1. And there is no space. If you fiddle around with different spaces here, you will never match power of mobility of this one with this one. Nevertheless, it turns out that if F is in LQ with Q is large enough, and B is here, and you have 1.4 with P0 equal to Q0 equal to d+1, then there is a solution U in W1 to P, and unique solution. And in that case, it turns out that this guy is in P. So, and at that point, I think I'm somewhat out of my time, although I started later than
yeah, maybe you have 1 more minute to conclude.
Yeah, and during that minute, I want to thank again the organizers, and thank you.
Okay, thank you very much. And so now let us move on to the discussion, which will be done by Mate Gerencha. Mate, are you here somewhere?
Hello,
Yeah.
I will share my screen, I guess. No, I cannot.
Cannot? Okay, just 1 second.
I think the problem is that Nikolai Vladimirovich is still sharing.
Okay.
No, actually,
Yeah.
I stop.
Yes, if you can start, Mate.
Okay.
Okay, very good. So our very last piece of discussion for this conference is done by Mate Gerencha, who works as an assistant professor at TU Vienna. Please.
Okay. Thank you for the introduction and for the invitation to this nice conference. So I will discuss, I would say a little bit tangentially what we heard in the previous talk. And so what I would maybe focus on a little bit more is considering the solutions of such equations, where so stochastic differential equations with irregular drift, where so they are driven by some Brownian motion B in d-dimensional. The diffusion coefficient is something reasonably nice. I don't want to really discuss too much details about the diffusion coefficient, so let's just assume that it's C2 and non-degenerate. And the main point will be the drift coefficient, which is far from Lipschitz, where, well, the reference is Lipschitz, because if sigma were to be 0, then of course the well-posedness of this ODE is basically requires B to be Lipschitz. But since we assume sigma to be non-zero, we can go far beyond that, and there's a long history of studying this phenomena called regularization by noise. Yes, so one thing, or kind of a series of works from which that we've heard from Nikolai Vladimirovich, which is this this last year, I think he had at least 5 or maybe more papers on this, and this is probably the last one that we heard about. And actually, this is what my question would relate to, is whether these Alexander estimates are already enough, or how far from enough they are to imply existence and uniqueness for solutions for this kind of drifts B. But in the discussion, I will be a little bit more tangential and actually mostly discuss things under the conditions which go back to Varatennikov, so which means just bounded drift. So we are not dealing with the bad integrability, and look at the following property of these solutions, that when you look at the proof of this existence and uniqueness, well, the way these solutions are constructed are not really constructive. So they either go through some Yamada-Watanabe argument or some compactness argument, and you might want to be more constructive or more practical, if you wish. And or just in general, you might want to ask how does do the discretizations of such equations look. So the most natural discretization of these equations is the Euler scheme, where this equation just defines the stochastic versions of the Euler method. So the kappa and t is just you have a grid of size 1 over n, and kappa and t is the last grid point before t. And if you look at how this xn behaves on the grid points, then this is precisely the Euler method, and in between the grid points, this is just a convenient extension. So this question was not asked by me. This was asked by István Gyöngy and Nikolai Krylov now 25 years ago, and they proved that basically under the conditions of Veretennikov, and of course there's a lot of technicalities that one could discuss, but let me just keep it at this level, so that for bounded B and for sufficiently nice sigma and non-degenerate sigma, the Euler approximations converge to the solution uniformly in time and in probability. So what I want to ask about these approximations is whether one can say a bit more than that, and in particular whether one can quantify this convergence. And well, so there's nowadays there's of course a lot of activity in studying numerical analysis of stochastic differential equations, and even in this subdomain. So in the case of drift, which are not Lipschitz, there's a lot of work, and again, this is just a small sample, so my reference list is always incomplete, so apologies if I miss anything. But despite all of this work, actually under this very simple setting, so that bounded drift and sufficiently nice diffusion, there was not even any known upper bound, as far as I know, for the Euler scheme until recently, and so this is work with Konstantinos Daraiotis and Koale, where we show that the rate of convergence is 1/2, which it's not only an upper bound, it's the upper bound, because this is kind of known to be optimal. In fact, I will get back to the optimality a bit later. So let me move a little bit of comparison to these existence and uniqueness results, and in particular to what we've heard in the previous talks, and what is similar and what is different. So one way that you can decompose the error is like this, and let's say stick to the additive case. So just basically add and subtract the integral of P of x and s, and then from the two terms, the second is something that is very similar to what you would encounter in uniqueness questions. So if you would be able to bound this for good enough processes, so good enough two processes x and xn, such an integral you can bound by x minus xn with some norm. I'm not writing norms because that's part of the question to find a good norm. Then you can get some kind of Gromval lemma argument or some contraction or something like this. And the same happens here, because if you can bound this by x minus xn, then you can get to a Gromval type argument, and you only remain with the first term, where we are using some new tools, which was already advertised by Peter a few talks ago. So this is a stochastic sewing introduced by Koale, and it's a very useful tool, and in particular bounding such quantities is in large generalities is very much possible with this. So in the interest of time, concerning LP drift, let me just mention, yes, please ignore please only focus on the last line, because I have not so much time. So let me just mention a very recent work where the approximation is considered where with LP-LQ drift, where the Euler scheme has to be modified because pointwise might not make sense to evaluate such a drift, where they managed to get some rate of convergence, but this is a weak rate of convergence. So this is, I would say, the strong rate is still kind of open in that case. And yeah, so the last thing I want to have a little bit time for is this optimality of the rate 1/2. So okay, how can you show that an approximation rate is optimal? The best thing you can do is if you multiply back, then you show some limiting object, and this is known. So this is a nice result by Jacob and Protter, where they show some kind of central limit theorem for the Euler approximation in the case of smooth coefficient, and that the limiting object is a V satisfying this equation. So there's a new noise term, the blue term. Yes, just like in the central limit theorem, you get some new normal variant bar. And okay, in the irregular case, you have kind of a problem that once B is starting to be far from Lipschitz, going back to this condition, then this gradient of B does not make too much sense to evaluate at xt. So the way to overcome this is something that might be familiar to some of you, is to concentrate not on making sense of gradient of B by itself, but of the gradient of Bxt dt. This is somewhat similar, although in, of course, much simpler setting than what happened in Nicholas's talk a few talks ago. And so what you can show is that if you take this integral process of the gradient B of x, you denote this by L. This is a well-defined mapping from, let's say, C1 functions, in which case the output is also C1. And then you can trade a little bit of regularity, or well, you can trade a lot of regularity. So you can trade almost a full regularity of B for a half regularity of the L. In which case the L is still 1/2 plus Hölder continuous. And then you can rewrite the equation for V with this green term now. And so what you get is a hybrid equation. So it has a Young integral part and stochastic integral part, or two stochastic integral parts. And okay, once you make sense of it, it's kind of trivial pose because it's just linear in V, or affine linear. And you can show that the Euler, so the central limit theorem holds for in this regime. So just be in C alpha. So this might be also of interest to people who are studying these hybrid equations, that this can arise in a very rather simple way, just from a central limit theorem for the Euler approximation. And with this, yeah, sorry, at this point I think I strayed a little bit far from the previous talk, but anyway, so thanks for the attention. And since I'm the last speaker, I also should thank the organizers for this very nice meeting.
Thank you very much, Mate. So maybe we can ask Karl Vladimirovich if he wants to pick this question. What do you think?
Do you want me to answer?
Yes, yes.
Okay. The thing is that once you get Alexandrov estimates, that there is a weak existence. About strong existence, it has nothing to do. This estimates has nothing to do with strong existence. But weak existence you get almost automatically by using Skarhot method.
And weak uniqueness?
but with weak uniqueness again, this estimates has nothing. No, they do have something to do, but very far. It's much more work needs to be done to get weak uniqueness. You have to somehow be able to solve this corresponding elliptic or parabolic equation, and this is Alexander estimate says that there is maximum principle for this equation, but if you know only that there is a maximum principle for an equation, then to say that this equation has solution and has nice solutions, because for weak uniqueness you need nice solutions, not only say, I don't know, bad, to which you cannot apply its formula. By the way, there is something interesting. I can prove for in many situations when B is summable to the power less than the dimension, I can prove that there exist. I can prove Alexander estimates, and I can prove existence of solutions. And I can prove that the corresponding elliptic equation has a unique solution W to D0. But I cannot prove that the solution of stochastic equation is weakly unique. I can only prove that solutions of the stochastic equation satisfying a conditional their green function exist, and these are unique. But maybe there are solutions which don't satisfy Alexander's estimate, and this is a question absolutely have no idea how to even approach it. So the situation becomes more and more complicated.
But maybe this is somehow related to, I don't know, what people see when they study SD, similar to what Mate presented, where Redrive B is a distributional. Then it's also you establish uniqueness only among a certain class of solutions which satisfies certain extra assumptions. So it's not.
Yes. Yeah.
Maybe this is related to this.
It does help. And by the way, this is not such a rare situation. Say in the theories of elliptic equations, even if you allow any solution, I would say let's consider this equation. Second order derivative is 0, and you allow any on the line from 0 to 1, and 0 at 0, 1 at 1. And you are saying, and I allow any solutions, differentiable only almost everywhere, for instance. Then the counter function will satisfy this equation, and it's not linear. So, so that indeed this situation appeared even in the theory of partial differential equations, that you have to have some restrictions on the class of your solutions. Although in probability theory, this looks like very artificial, that they are unique only if they satisfy certain estimates. Well.
Okay. Yeah, thank you. Are there any questions from the audience to our two speakers? Okay, if not, then maybe I can ask Mate a question. So in your results, so do you use only stochastic swing ideas or these Zwonkhin transformations ideas as well? Like especially your last
for
result?
this, we use Zwonkhin transformation. So these things that I presented here don't work for fractional Brownian motion. Only this kind of first part is what we can do for fractional Brownian motion, but anything other parts we use Zonkin transformation.
No, and your very last result with central limit theorem, so it's also based
Also, yes.
on some Zonkin transformation. Okay. And do you use stochastic sewing or is just pure PD technique?
We use stochastic sewing as well. Yeah, so it's kind of a mix.
Okay, yeah, that looks very interesting. Okay, so any other people have any questions, comments?
I just want to add a comment that well, if your coefficient is on the continuous, then everything works fine with the stochastic sewing. But the problem that we are thinking of was when the drift is has some sort of left regularity, then we have to go through the Zonkin transformation. But as it is stated here in this theorem, then this result can be done by stochastic sewing.
Okay, yeah, thanks for clarification. Okay, any more comments? Okay, then if not,